So we're going to be thinking about what happens when you evaluate polynomial functions for very large positive numbers and very large negative numbers. And how does that manifest on a graph? So we're going to investigate. So question A, if this was a polynomial that was x to the fifth, what would happen if I plugged in 100 for x? So what's 100 to the fifth? Is it positive or negative? That's all I care about. It's positive. What about negative 2 times 800 to the second?
Negative.
Negative. Negative 6 times negative 900 to the fifth.
Negative. No, negative.
Just keep guessing both until you get it, right?
Negative. It's negative. Would you square a negative?
So we're not squaring the negative. We're raising a negative to the fifth power. So a negative raised to the fifth power would be negative. And then times a negative would be... So this one's positive. Negative 100 to the fourth. And negative 230 to the 17th.
Negative.
Can everybody figure those out? Hopefully.
So if it's odd, it stays the same.
Sure.
If it's even, it's always positive. That's not.
The exponent. The term with the exponent.
Multiply it by negative.
The term with the exponent. Good catch.
Grades 7 through 12, your progress reports are ready this morning. Ms. Biddle has them if you want to send someone to the high school office to get them. Thank you.
Number 2. Consider f of x equals x cubed plus 5. What happens to the y values as x gets bigger and bigger? So let's just investigate. So what if x was 100? So that would be 100 to the third. That would be something that is positive. Yeah. And then if I add 5 to it, it's just going to get a little bit bigger, right? So this term doesn't do much. That's what they're wanting you to see. That this term dominates as the x's get bigger. Just imagine if I plugged in 1,000. So 1,000 to the third. That's an even bigger number. And this 5 matters even less. Right? So this term goes away. This is the term that dominates as we tend towards infinity. As we plug in bigger and bigger values.
So what if we add infinity? What if we do x to the third plus infinity?
Well, you can't add infinity.
What if we added 3,000 Google flags?
The x to the one with the exponent would dominate at the large ends.
I don't understand that.
Because there's way bigger numbers than what you just named. Right? So no matter what number you name, I can name way bigger numbers.
Tree of 3?
I can name a way bigger number.
What's bigger?
I mean, that I don't have to know the name for it, but there's an infinite number of numbers past your number. No matter how far you go up. Yeah. So that's why at the infinities, constants don't matter. The highest powered term is the one that matters, which in this case is x to the third. So what happens to the y values as the x values get bigger and bigger? The y values tend towards infinity. Is it okay if I use the symbol for infinity? All right. What happens to the y values as the x values decrease without bound? So as my x values get smaller and smaller.
They tend toward negative infinity.
Yeah. So like if I plugged in negative 100, right? Negative 100 to the third would be some large negative number. And if I add 5 to it, it's still some large negative number, right? And as I keep plugging in more negative numbers, it's just going to get closer and closer to negative infinity. So we would say here the y values tend towards negative infinity. So here we're going to actually plug in some values to see what happens. Because what happens if I use this one? Now I have an x to the fourth term and an x to the third term.
Excuse me, teachers. Sorry for the interruption, but we did have a little bit of an issue printing for students who go to tech. So if you have a student that has first and second tech or third and fourth tech, and they do not have a progress report with you, those students can come by the office to get their progress report. Thank you.
Okay, so we have our graphing calculators. Let's plug this in for our y equals. Because, again, this one's different because we have two terms with an exponent. And so, like if I plug in 3 for x, it's not super clear what would happen, maybe. Maybe it's not super clear to you guys. So you have this plugged in for your y equals. All right, go to the table. So second table. And so you should start with what? An x value of 0. Hopefully everybody's got x at 0 on their table. And then what happens as the x's increase?
X is increased, the Y is also increased.
The y's are increasing, and as you continue, does that pattern hold true
Yeah.
as you keep going? Okay. So,
They get bigger and bigger and bigger and bigger.
okay. So, what would you say is going to happen to the y values as x gets bigger and bigger? The y values,
Are getting bigger and bigger.
and let's say it more fancy,
Tend toward infinity.
tend towards infinity. And now in the other direction, what happens when the y to the y values as the x values decrease? It gets smaller.
Like, doesn't that just go for any, like,
Y values tend towards 0.
any positive, like, function?
They don't go to negative infinity, right?
They go to, they're still positive.
What do you mean?
Like, if the slope is positive, doesn't that,
Yeah.
that goes for that.
And they're still.
So let's don't say for functions, because we do have functions that don't tend towards infinities at the end. But all polynomials, so things that look like this,
That are positive, always the Y values tend towards infinity.
or negative infinity. Yeah, if this is positive, if the a value, yeah. Yeah. That's kind of what we're,
That's kind of why I was confused, I was like,
that's kind of what we're pointing towards. But like, so what do we say happened here? Sorry, let me answer that one first. Before I get
Y
it.
values tend towards 0.
They tend,
Why?
They tend towards infinity.
Why'd you get 0?
Because it can't go negative because it's x to the 4th.
What can't go negative? The y values can't, but the
Y
x's,
value-
the x's can go negative. I can plug in anything.
So Y values can't go negative, so
They're
Y
going
values
positive.
tend,
Yeah, they're going positive.
they're still going positive?
Because when I raise them to the fourth, they become positive, which means they're going to be a very large.
Tend to go positive.
they
Tend
tend
towards, tend
infinity
toward infinity.
at the bottom too, because it's a,
Don't say that. What do you mean bottom?
Huh?
You said at the bottom. What do you mean at the bottom?
the second one, B.
Oh, okay. Okay.
Because it's a parabola.
Ain't nobody getting a mesh.
Okay. What would happen if we changed the leading coefficient to be -3 instead of +3?
Wouldn't matter.
It wouldn't matter. Let's see. Change your y equals. Do you guys know how to insert a negative? You can do second delete, and that inserts it. You can put a negative at the front instead of erasing everything.
It literally does nothing, huh?
If you do second insert and then hit the negative button, you wouldn't have to type the whole thing back in.
And they're all negative.
Or you just.
The Y values tend towards negative infinity.
What?
Yes.
No.
Yeah.
No.
Because what's x what's getting raised to the fourth power? The negative 3 is not getting raised to the fourth power. So if I plug in 10,000, 10,000 to the fourth is a really big positive number. And then times that by negative 3. So it becomes an even bigger negative number, right? Order of operations.
That is true.
Yep.
I forget that 3's not in the.
Okay. Appreciate it.
Yeah.
So we would say as x gets bigger.
If we change the x to negative, it wouldn't change it.
It would also tend to get to -0.
No.
Yes.
If we change x to negative.
Okay. So let's plug in negative 10,000.
Yes.
So what's negative 10,000 to the fourth?
It's the same as 10,000.
It's a very big positive number.
Yes.
Then multiply that by negative 3.
No, I'm talking about if we just changed x and didn't change 3 on number.
Yeah, we agree.
Yeah.
We agree. On this one, when the a value was positive 3, plugging in a negative, got a really big positive number times 3, it was still a really big positive number. So that one did tend towards positive infinity.
But also as the axis gets smaller, the line.
And so as x gets smaller,
It also.
y, I shouldn't have said changes in the last one. Y tends towards, sorry, I must have got distracted. I don't know how that might have happened.
So they both go to -2.
They did.
So the leading coefficient, like base part is positive, the y value is gonna tend towards infinity. Like,
Oversimplification. There's another rule you're leaving out. We'll talk about it in just a second. So, what I want to do at this point is we are fixing to introduce what's called limit notation. You don't necessarily know how to take limits of things yet, but limits is a big deal in calculus. And they want to introduce you to the notation in Precal. So that way you kind of understand what it is you're looking at. And you will have a question on the test that requires you to answer in limit notation. Both on the test we have coming up for Unit 2 and for your AP exam at the end of the year. There's a free response portion that requires you to do exactly what we're fixing to do. Okay? It's not difficult, but people just get confused because they look at it and they go, I've never done this before, so I just want to be confused. Okay? But it's not that bad. So here's how it looks. The x values are getting bigger and bigger. Okay? X values are getting bigger and bigger. So this is what we would say. We would say the limit I'm going to scoot over some more. I don't have enough room. So I'm doing number 2. I'm going to say the limit as x approaches infinity of f of x is equal to infinity. That's limit notation. So let me talk through what this is because I know it looks weird on here. This is limit as x approaches. That's an arrow. Okay? I know my arrows don't look very good. The limit as x approaches infinity of my function f of x is infinity. So what I'm saying is, as the x values get really big, the y value gets really big. Right? That's all that's saying. But it's just written in a special notation called limit notation. So let's do b together for 2b. What do you think that would look like? Limit. So what's happening to my x's? We're getting very small. So as the x approaches negative infinity of my function named f of x,
Equals negative infinity.
that's it. As my x's get really small, the y's also get really small. Okay, you guys do 3a and b. Write those in limit notation. Well, sorry, do all of 3. Do 3a, 3b, and both of them in 3c. And pay particular attention to the name of the function, right? I said the limit as x approaches infinity of f of x because we were talking about a function named f of x. This function is not named f of x. It is named g of x. Told you people would get confused because they want to be. You want to be confused?
I don't want to be confused, but I am. I don't know how.
Mm-hmm.
I'm not a smart guy. Well, I am a smart guy. I just don't. Not in this class.
I feel you.
Might be the smartest one. So I might just be the smartest one.
Oh.
No, I'm cooking.
Yeah.
Some stuff. Especially because they're the smartest one. Some stuff.
Is there anybody that wasn't here yesterday that didn't fill out one of these credit forms?
I did not get a progress report.
You didn't get one? You got a tag?
Well, if we had Brandon,
I don't have one for you. Sorry. You can go ask an office.
Progress there.
I made some good progress.
All right, are we finished?
Yeah.
3A.
no, we're not finished.
You're not finished.
Well, I'm not gonna get finished because I don't know how to do it. I'm just gonna wait.
Oh, brother. I don't understand because I don't want to understand. I choose not to understand.
Not understand.
Okay?
Because I do not understand.
Well, let's do 3A together. Tell me, it should be the limit. That's how we start.
I don't know what that is.
That's just notation. You don't know how to formally take a definition of a limit? Just think about what we've been saying. What do the y values do as the x's tend towards something? That's all that we're doing. We're just writing it in a notation that you would use if you took calculus. You don't formally understand what a limit is. I'm not getting into what a limit is. But we're just going to write it in this form.
When Rock gives you limits, you make questions.
Lemonades. Okay, if I've got the limit. So what's happening to the x's in 3a?
3A.
X is
They're
go
getting
up.
bigger.
So I would say x approaches infinity.
Okay.
What's my function name? G of x equals, what are the y's doing?
Going towards infinity.
It's a fill in the blank, Jack.
That's correct. For right now, limit notation is a fill in the blank system for you.
Jack, alright, start off by writing lim, and then under that write x with an arrow, and then beside lim to the right, write g of x, or whatever your function.
The only things you're going to change every time for now is here, here, and here. Yeah, I appreciate that. B, what's happening to the x's?
They're going
X
down.
go down,
Approach.
negative.
X, arrow, negative.
So we're approaching negative infinity of the same function.
G of x equals infinity.
So as the x's get small, the y's still go to positive infinity.
I like this.
No kidding.
I just didn't know how to do it.
C, we've got two of them. So the first one is talking about as the x's get bigger is my first statement.
You got big and small?
So the limit as x approaches infinity of, this one was still named g of x,
And then negative infinity.
was negative infinity. And then as the x's got smaller, so the limit as x approached
Negative infinity.
negative infinity of g of x is
Negative infinity.
questions. So again, you don't have to know what a limit is yet. That's not what this lesson's about. The lesson's about the notation and understanding what happens as x gets really big and really small. That's our goal. Okay, looking at number 4, they've graphed two functions. What's interesting here is these functions are the same parent function. Right? This is an x to the 5th polynomial, and this is an x to the 5th polynomial. All right? Okay, sorry, I about said which was which. Without putting in your graphing calculator, let's see if you can guess which is which. So which of these is G and which of these is H on the graph?
Can I say
H
that
is
loud?
the dotted line.
H is the dotted line.
That's correct. Why? How did you know that?
Because
Negative
there's
10,
minus
the
10.
x goes down.
And the Y.
Oh,
is
sweet.
that.
That's smart. That ain't what I was thinking. I love it. Okay, so H has a y-intercept at negative 10. So that means it has to cross the y-axis at negative 10. Sweet. Okay, so to me, I was thinking differently. I was thinking this is a more simple parent function. Just the basics without the bells and whistles. This one has some more interesting stuff going on here, right? So which of these has more interesting stuff? Definitely the dotted one. Right?
It's
It's got
got a little-
crazy turns.
It's
Yeah.
got a little wrapper.
It's got a little bit more interesting dynamics. But the y-intercept's a great spot because that's what you should have known. Perfect. Yes, I'm fired up. That's like progress. Okay, so the dotted one is H and this solid one is G. If you had to compare the end behavior of the two graphs. So that's what we've been doing this whole time. We've been comparing end behavior. So what happens when the graph approaches its end? Which there is no end, so that's kind of weird, right? But as the x gets really big and the x gets really small, what's happening? So let's talk about H. Let's talk about G. Let's talk about G. G. As the x gets really big, what are the G values doing?
Drop it.
They're getting really small.
Really small. So they're going towards negative infinity. What about when the h's approach as x goes to infinity? For h, the y's are also going to negative infinity. So they have the same end behavior when x gets really big. Right? They're doing the same thing. What about when x gets really small?
It gets really small.
They're
No, it gets
Y going to.
They're both going to positive infinity. So they do the same thing as x gets really small.
They're
As
the
well.
same beanie.
So they have the same end behavior.
Yes.
How do they have the same end
Because they're
behavior?
both odd exponents.
But one's going down and one's going up.
They're doing the same thing.
I'm not comparing the two end behaviors of G. I'm comparing the end behavior to each other.
It's because they're the same.
I know what he's saying. As G gets big, as the x's get big on G, the y's go to negative infinity.
And it also happens on H.
And it also happens on H. These are not the same. I'm comparing them to each other, not to itself. So what is that end behavior? As the x goes to infinity, the y's go to negative infinity. And as the x goes to negative infinity, the y's go to positive infinity. So I could have written that in limit notation again, but I didn't have enough space, so I was really being lazy. Okay? But I'm saying the same thing. And question 5. What term in the polynomial seems to have the biggest impact at end behaviors? So like right here, h has 3 terms. Which of these terms has the biggest impact on the end behavior?
And the first A,
Why?
because it's negative. And
Not
it's-
because it's negative.
because it's got 5
It's got
exponents.
an all big.
Has the biggest exponent. The term with the biggest exponent wins. Okay, it always wins at the infinities. And you can see here, these have the same leading term. And so look at what these graphs do at the end. The same thing, right? They do some different funny business in the middle, but as we tend towards the infinities,
We get dinged.
they do the same thing.
I don't understand the part when they 2x to the 5th is, that's the biggest coefficient, because the other one has the same.
Not coefficient.
Or exponent.
So right here, this is its own polynomial. So what term has the biggest exponent? There's only one term. So this is the biggest exponent. Here, this one has 3 terms. But what term has the biggest exponent?
Negative, please.
The 5th. So
But since it has other things with it,
It has 1 to
the
4.
other things make it do its funny business in here. That's why we have a different y-intercept. We have this local max. We have 2 more x-intercepts. All of that comes from this term and this term. Make it do some more different things in the middle. But at the ends, when I get really big x's, they do the same thing. And when I get really small x's, they do the same thing. That's because this leading term rules the day at the infinities. But in the middle, in the meat of your graph, it can do all sorts of random things with other terms.
-10 needs to show us work.
Does that answer what you were asking? Okay.
You know? -10 should be minus.
So I want to make sure I wasn't missing anything that I was supposed to go over. I just got lazy and didn't want to print it. So here it says, for very large positive and very large negative input values, which is at the ends of the graph, the polynomial behavior is dominated by the leading term. We pretty much discussed that. Learning target, that's 1 and 2. Learning target 3 says polynomials have unbounded end behavior. So what that means is as x's get really big and the x's get really small, it's always going to go to either positive or negative infinity. Polynomials do. That's not true of every function, but it is true of every polynomial. They don't have bounds at the end.
We learned about this last year. The even and odd with the end behaviors. We learned about that.
Yep.
It was easy.
We didn't learn about it. We did quizzes and stuff. We didn't learn anything.
Oh my god. Jack.
I'm recording. Okay, so from here, this is what you guys were trying to formalize. Your like little cheat sheet where y'all are trying to say what happens. So when the degree is even of the polynomial, right? So it's degree 2 or 4, 6, 8, 10. The end behavior agrees. It either goes to positive infinity on both ends or negative infinity on both ends. But end behavior agrees when the degree is even. How do I know which one it is, either up or down? The leading coefficient. So if we look at the number in front of our leading term, If it's positive and it's even, we're going up. That's why this says positive, right? Leading coefficient is positive and it's even, we're up. If the leading coefficient was negative and it's even, we're both going down.
Because even stays the same at the end, odd is different at the end.
That's correct. Even powers always have agreeing in behavior. Either both up or both down.
Yes.
Odd degree polynomials have disagreeing in behavior. One's positive, one's negative. Okay? By default, the x's should be, the y should be increasing as the x is increasing. That's the default. If you think about what does x to the first look like? Here. What does x to the third look like? Here, right? So that's the normal in behavior of an odd degree polynomial. But if I reflect it, if I have a negative leading coefficient, it changes the in behavior to be decreasing from left to right.